When the Norwegians decided to drill 24 kilometers through Scandinavia's largest glacier, they knew it would be difficult. What they didn't expect was that this project would become one of the greatest engineering challenges of the 21st century. Today, I'm going to tell you how they did it, and why it almost went completely wrong. This is the Lærdal Tunnel in Norway. It connects two important commercial routes that were previously separated by the Folgefonna glacial massif. In winter, these communities were practically isolated. The conventional road over the mountain closes for 4 to 5 months due to snow. The project began in 1990, but construction only started in 1995. Why the delay? Because no one knew how to drill through 200 meters of permanent ice without causing disasters. The glacier isn't just solid ice. It's a dynamic structure with underground rivers, cavities, and variable pressures. The internal temperature varies from 15 degrees below zero at the surface to up to 2 degrees below zero at the bottom, where pressure partially melts the ice. The biggest challenge? Ice melts with heat, but drilling generates exactly that. Imagine trying to cut cold butter with a heated drill. It melts, lubricates, but also creates vapor pressure that can explode. The solution was a unique tunnel boring machine, the Robin's main beam. It cost 52 million euros and weighed 850 tons. Unlike conventional ones, it had an integrated cooling system that kept the cutting temperature always below 5 degrees Celsius. The technology: spray nozzles sprayed a mixture of water and antifreeze directly at the cutting point. The drilled material was instantly sucked through pneumatic tubes, avoiding accumulation that could cause pressure. They developed the drill and chill method: drill 2 meters, stop, cool the area, remove material, install temporary support, advance. Each cycle took 4 hours, maximum speed, 6 meters per day. During drilling, a team of geologists analyzed each collected fragment. They could predict changes in ice structure 50 meters before the tunnel boring machine arrived. The monitoring system was more precise than those used at NASA. 300 sensors measured temperature, pressure, vibrations, and air composition. Any anomaly triggered automatic protocols. Each worker wore a suit with GPS sensor and direct communication with the surface. In case of emergency, they had pressurized shelters every 500 meters, essentially survival capsules. In 1997, the tunnel boring machine encountered a layer of pressurized water between the ice. In seconds, 150,000 liters flooded 400 meters of the tunnel. The water was at 4 degrees Celsius, warm by local standards, but enough to damage equipment. The solution was ingenious. They injected a special chemical foam that expanded and solidified on contact with water. It created a temporary barrier while they pumped the water out. Ventilation in an ice tunnel brings unique challenges. Air too hot melts the walls. Air too cold condenses moisture that turns to ice on equipment. The solution? A 3-stage system. External air is preheated, humidified, then cooled to exactly 8 degrees Celsius before entering the tunnel. 40 monitoring stations ensure the temperature never varies more than 2 degrees Celsius at any point. In March 1998, the worst accident happened. A section of ice destabilized by drilling vibrations gave way. 3 engineers were trapped when 20 tons of ice blocked the tunnel. The rescue lasted 14 hours. They used controlled micro-explosives and hot water jets to open passage. All 3 survived, but 1 sustained permanent injuries. This accident changed all safety protocols. After the accident, they implemented the Smart Ice System. Fiber optic sensors installed in the ice detect micro-cracks. Algorithms predict collapses with 87% accuracy up to 72 hours in advance. They introduced Explorer robots that test each section before human passage. They're essentially small tanks that map resistance and temperature in real time. In 1999, they started simultaneous drilling from both sides. The challenge? Meeting in the middle with millimetric precision. In 24 kilometers, the accumulated error couldn't exceed 10 centimeters. They used an underground GPS system with reference stations on the surface. Measurements were taken every 100 meters using equipment that cost more than luxury cars. In 2000, they discovered methane pockets inside the ice, remnants of organic decomposition from thousands of years ago. Methane plus sparks, feats explosion. Simple as that. They developed a forced ventilation system specific for gases. Chemical detectors every 50 meters, if they detected 0.75% methane, well below the explosive limit, the entire sector was automatically evacuated. In November 2000, the two teams met. The final precision, 17 centimeters horizontal difference, 8 centimeters vertical. In 24 kilometers. To compare, that's like hitting a 50-centimeter target at a distance of 100 kilometers. The moment was broadcast live on Norwegian TV. Two drills touching through the ice represented one of the greatest precision feats in civil engineering. In the last kilometer, they found something unexpected. A natural ice cave with unique crystalline formations. It was an 8,000-year-old ecosystem perfectly preserved. Difficult decision: destroy to save time and money, or preserve? They chose to preserve. They redesigned the tunnel to bypass the cave, which today is a glaciological research center. The tunnel was inaugurated on November 27, 2000. Total cost, 1.2 billion euros. Construction time, 5 years. Fatal accidents, 0. Today, 1. 5 million vehicles pass through annually. It reduced travel time from 4 hours to 20 minutes. More importantly, it developed technologies that are now used in Arctic projects around the world. This tunnel proved that with careful engineering, it's possible to overcome even the most hostile environments. And sometimes, the greatest technical challenges teach us more about preservation than about destruction. Do you know any engineering project that changed an entire region? Tell us in the comments. And if you enjoyed the video, subscribe to the channel. There's much more extreme engineering history coming.